Imagine trying to understand a bustling city from an airplane. You can see the major highways and districts, but you miss the individual conversations happening on street corners, or perhaps you can hear every whisper in a single building but have no idea how it connects to the rest of the city. How do we choose the right lens to truly see the brain's incredible activity? When it comes to brain mapping, the fundamental trade-off is between spatial resolution, which is how precisely we can pinpoint activity in space, and temporal resolution, which measures how accurately we can track changes in activity over time. Achieving high resolution in both dimensions simultaneously is extremely challenging, meaning you often have to prioritize one over the other. This inherent compromise stems from the physics and engineering limitations of our current neuroimaging technologies. Techniques like functional magnetic resonance imaging, or fMRI, offer excellent spatial resolution, allowing us to see which specific brain regions are active down to a millimeter scale. However, the signals fMRI detects are indirect, relying on blood flow changes which are much slower than actual neural firing, limiting its temporal resolution to several seconds. Conversely, electroencephalography, or EEG, directly measures the brain's electrical activity and provides exquisite temporal resolution, capturing neural events in milliseconds, but it struggles to pinpoint the exact location of this activity deep within the brain, giving it poor spatial resolution. To navigate these trade-offs, researchers carefully select their brain mapping tools based on the specific questions they are trying to answer. If you are studying where memory formation occurs, fMRI might be your best choice. However, if you are investigating the precise timing of a sensory response, EEG or magnetoencephalography, or MEG, would be far more appropriate. Often, a multimodal approach combining different techniques, for instance, simultaneously using EEG and fMRI, is employed to leverage the strengths of each method and overcome their individual limitations, creating a more complete picture of brain activity. Understanding this resolution dilemma reveals the complexity of bridging the gap between macro-scale brain function and micro-scale neuronal dynamics. A key concept here is the inverse problem in neuroimaging, particularly for EEG and MEG, where inferring the precise source of an electrical signal from recordings on the scalp is mathematically challenging and inherently ambiguous due to the brain's intricate structure and the conductive properties of its tissues. This inverse problem is a fundamental reason why achieving both high spatial and temporal resolution from non-invasive methods is so difficult. Ultimately, the choice of brain mapping resolution is not about finding one perfect technique, but rather about strategically combining tools and understanding their inherent strengths and weaknesses. It is about aligning the capabilities of the technology with the specific scientific question at hand, allowing us to accurately observe the brain's dynamic processes and localized functions, bringing us closer to unraveling the mysteries of the mind.